Okay, let's unpack this. For centuries, humanity has lived up at the stars and asked one of the most profound questions imaginable. Are we alone? It's a query that has fueled countless hours of scientific research, philosophical debate, and let's be honest, a good chunk of our favorite sci-fi. Today, we're taking a deep dive into the astonishing quest to answer that very question. We're talking exoplanets, those incredible worlds spinning around stars far beyond our own sun. We'll explore the groundbreaking ways we're finding them, how our telescopes are giving us surprising hints about their environments, and what these tantalizing signs of life we keep hearing about actually mean. And here's the kicker. Will we ever truly know if life exists out there without literally, going to these distant worlds ourselves? It's a journey from distant starlight to the dreams of star-hopping probes.
It's an incredible time to be exploring this. We've really gone from merely speculating about other worlds to confirming thousands of them. Our mission today is to dig into what those detections really tell us, the exciting breakthroughs, the significant limitations, and what the latest research papers and articles reveal about the path ahead.
So let's kick things off with the sheer scale of discovery. It feels like every other week there's a new exoplanet announcement. Just how many of these incredible worlds have we actually found?
You're absolutely right. The numbers are truly astounding and, well, constantly growing. As of late July 2025, we've confirmed over 6,000 exoplanets.
6,000! Whoa!
Yeah, more than twice the number of planets in our own solar system.
6,000! That's not just a number, that's a whole new universe of possibilities opening up. And get this, almost all of these are within our own Milky Way galaxy, right? But I heard there's even hints of planets outside our galaxy.
That's right. Most are within the Milky Way, but there is some early suggestive evidence for extragalactic planets, too.
Wow. So planet formation might just be everywhere.
It certainly suggests it's a universal process, yeah. Fundamentally alters our perspective on how common planets might be.
And speaking of common, how close are our nearest neighbors? Are we talking about worlds that are relatively within reach, cosmically speaking?
Well, within reach is relative, but the nearest confirmed exoplanets orbit Proxima Centauri,
Proxima Centauri, okay.
which is just 4.2 light years, or about 1.3 parsecs from Earth. Astronomically speaking, that's practically right next door.
Right next door, yeah. Makes it a prime target for future study then.
Absolutely.
So how exactly are we spotting these distant worlds? I mean, they're tiny, they're incredibly far away, and their host stars are so bright. We can't just point a telescope and see them directly most of the time, can we?
Precisely. The challenge is immense, but the ingenuity of the methods we've developed is pretty immense, too. Most exoplanets aren't directly seen. Instead, we use these incredibly clever indirect methods, basically observing how the planet affects its star.
Okay, indirect methods, like...
The two main workhorses are the radial velocity method and the transit method.
Let's pull back the curtain on those. Radial velocity first. How does that work? Sounds complex.
Well, imagine you're watching someone walking a dog, but you can only see the person.
Okay.
As the dog pulls on the leash, the person would wobble slightly back and forth, right?
Mm-hmm.
The radial velocity method is kind of like that. It detects the tiny wobble in a star that's caused by the gravitational tug of an orbiting planet. As the planet pulls the star moves slightly towards and away from us here on Earth.
Ah, so you're seeing the star move, not the planet.
Exactly.
Mm.
And that movement causes its light to shift, slightly blue shifted as it moves toward us, red shifted as it moves away.
Mm.
By measuring these tiny shifts, we can figure out the planet's minimum mass and even the shape, the eccentricity of its orbit.
Fascinating. And you said it works better for some stars.
Yeah, it's particularly effective for detecting planets around low-mass stars.
Yeah.
Their wobble is just more pronounced, like a smaller person being pulled by a big dog.
That's a great analogy. Okay, so that's the wobble method. What about the transit method? That sounds more like something passing in front.
It is, yes. It's maybe a bit more intuitive. You're basically observing a slight, often really tiny dimming of a star's light.
Ah, when the planet crosses in front.
Exactly. As the planet transits, or passes directly between us and the star, think of a tiny fly crossing in front of a distant streetlight. This requires incredibly high-precision cameras, very low noise, and what we call high-duty cycles, meaning they stare almost continuously.
To catch those tiny dips.
Precisely. Those minute dips in brightness.
So if you can observe a planet with both methods, the wobble and the dimming, what does that tell you? More info.
Oh, absolutely. When you combine both radial velocity and transit data for the same planet, you can determine its true mass, not just the minimum. And knowing the true mass, plus the size from the transit depth, gives you its density.
Density, so you can start to figure out if it's rocky like Earth or gassy like Neptune.
Exactly. It's a huge piece of the puzzle.
Yeah.
Is it potentially a terrestrial world?
And what kind of cutting-edge instruments are making all these discoveries possible? Must be some serious hardware.
Oh, definitely. We've had a whole series of powerful telescopes, both on the ground and in space. Early missions like Karat and the famous Kepler mission really paved the way.
Kepler found thousands, right?
Thousands, yes. Then its successor, K2. Hubble and Spitzer also gave us early insights. And now we have TESS surveying the whole sky, SHIOPS doing follow-ups, and the upcoming Plato mission is really exciting too. Direct imaging, actually seeing the planet, is still quite rare though.
Right, you only see the big ones far out.
Typically, yeah. Large planets, often around young, massive stars, or things like sub-brown dwarfs that are far from their host star, like
Yep.
2M1207b. But these indirect methods, they're revealing a universe absolutely teeming with planets.
Okay, this is where it gets really interesting for our search for life. The concept of the habitable zone, often called the Goldilocks Zone. We hear about it all the time, but what exactly is it?
It's a crucial concept. The habitable zone is basically the region around a star where the temperatures are just right.
Just right for what?
Just right to allow liquid water to potentially exist on a planet's surface. Not so hot it boils away, not so cold, it's permanently frozen solid ice.
The just right sweet spot, like Goldilocks porridge. Got it.
Exactly.
And what determines where that zone is? It can't be the same distance for every star, surely.
Oh, definitely not. It's incredibly dynamic. Key factors are the star's size and age. A bigger, hotter star has its habitable zone further out. A smaller, cooler star, much closer in.
Makes sense.
But it's more complex than just that. The planet's atmosphere plays a huge role. Does it have a greenhouse effect trapping heat?
Right, like Venus versus Earth.
Precisely. And even the planet's mass can influence it. Larger planets might hold on to thicker atmospheres, potentially widening the zone where liquid water could be stable.
So what does this all mean for our search? Finding a planet in the habitable zone. Habitable doesn't automatically mean inhabited, does it? It feels more like potential.
That's a critical distinction, absolutely. Habitability is a prerequisite, but it is absolutely not proof of life. Our telescopes give us clues about a planet's environment, which helps us understand its potential for life. So the search for potentially habitable exoplanets mostly focuses on finding those terrestrial, rocky planets within this Goldilocks zone. They seem the most likely candidates based on life as we know it.
Right. Now, if we can't visit these planets directly yet, we're relying on remote sensing to look for these whispers of life. When we talk about signs of life, what exactly are we trying to spot from light years away? What are these biosignatures?
Biosignatures, yeah, we're looking for gases or maybe surface features or even changes over time. Things that are produced by living organisms and detectable remotely.
Like cosmic fingerprints of life.
Kind of, yeah. Think of it as forensic science on a galactic scale.
Okay, so give us some examples. What specific things are scientists hoping to find in, say, an exoplanet's atmosphere?
Well, on the gaseous front, the big ones are molecules like oxygen O2 and its cousin ozone, O3. On Earth, these are overwhelmingly produced by photosynthesis.
Okay, oxygen and ozone. What else?
Methane, CH4, and nitrous oxide, N2O laughing gas are also key targets. Life produces a lot of those here. Then there's some more maybe exotic ones, dimethyl sulfide, DMS, methyl chloride, CH3Cl. Even phosphine, pH3, has been discussed.
Right.
Gases that, on Earth, are strongly linked to biological activity.
And beyond gases, are there other kinds of signs?
Yes, surface biosignatures are another possibility. A prime example people talk about is the vegetation red edge.
Vegetation red edge. What's that?
It's a distinct spectral signature. Chlorophyll in plants absorbs visible light strongly, but reflects near-infrared light very effectively. So our green plants actually look very bright in infrared photos. Finding that sharp edge in a planet's reflected light could suggest widespread plant-like life.
Wow, like seeing forests from light years away.
Potentially, yes. Or maybe other pigment features, or even polarization signatures, how light reflects off surfaces. And then there are temporal biosignatures. Think seasonal changes.
Like CO2 levels going up and down.
Exactly. Like CO2 being consumed by photosynthesis in the summer and released by decay in the winter. Or maybe variations in albedo, how reflective the planet is as vegetation grows and dies back.
The sheer wonder of this is that our current tools, especially the James Webb Space Telescope, JWST, are actually giving us these unprecedented views into exoplanet atmospheres. It feels like we're getting closer to spotting these whispers.
Indeed. JWST is incredibly powerful. It can detect objects 100 times fainter than Hubble could, and it operates across a really useful range of infrared wavelengths.
Perfect for sniffing out those atmospheric chemicals.
Precisely. It's revolutionizing how we characterize these worlds.
And JWST has already made some headlines, hasn't it? Especially with a planet called K2-18b. What was the story there?
IS K2-18b. It's a particularly interesting target. It's a sub-Neptune exoplanet, maybe an ocean world, about 124 light years away. JWST detected carbon dioxide and methane in its atmosphere, which was already exciting. But then initial reports announced the possible presence of dimethyl sulfide, DMS.
DMS, didn't you say that was strongly linked to life on Earth?
Yes, the initial reports came with a pretty significant claim that on Earth this is only produced by life. So you can imagine the excitement.
Huge. That sounds like a massive potential breakthrough. But I remember hearing some follow-up studies introduced a bit of caution. How do we avoid, jumping the gun, declaring life when maybe it's something else?
You've hit on one of the greatest challenges in astrobiology, false positives. Subsequent studies question whether JWST's instruments, given the noise in the data, could reliably tell DMS apart from methane, which was also present. Other research also pointed out potential abiotic sources for DMS non-biological ways it could be produced. It highlights a crucial lesson. Morphology alone, just seeing a shape or a chemical signature that looks like life isn't enough. It's just too easy to be fooled by non-biological processes mimicking life.
That makes perfect sense. Are there other examples, maybe closer to home, that taught us this lesson, these false positives?
Oh, definitely. A classic example is right here in our solar system. Methane, ozone, and even oxygen have all been detected on Mars.
Really? Oxygen on Mars?
Tiny amounts, yes. And ozones have been found on Venus, too. Initially, these were considered potential biosignatures, but now they're largely attributed to abiotic photochemical processes, basically. Sunlight interacting with the atmosphere, breaking down molecules like CO2 and water vapor, and creating these gases without any life involved.
So sunlight can mimic life signatures. Wow.
It really underscores the need for extreme rigor. You have to rule out the non-biological explanations first.
Okay, so it's not just about finding gas, it's about the whole context. It sounds like the scientific community has a really rigorous framework now to assess these extraordinary claims. How does that work?
Absolutely. It's moved way beyond just spotting one gas. It's a multi-layered approach, often using Bayesian statistics, basically assigning probabilities based on all the evidence. It demands multiple lines of evidence.
Multiple lines. Okay. What are the steps?
Well, there are roughly 4 key components. First, you have to thoroughly characterize the star and the whole planetary system, star's age, its spectrum, the planet's mass, its radius. You need the background context.
Setting the stage.
Exactly. Second, you characterize the planet itself, its climate, its potential internal processes to really evaluate its habitability. Is liquid water truly possible? Third, within that context, you search for potential biosignatures, looking for consistency. Does finding methane make sense given the planet's likely geology, for example? And finally, the fourth and absolutely critical step, exclude all plausible abiotic false positives. You have to try and explain it without life first.
All plausible ones. That sounds incredibly difficult.
It is. And only after you've done all that can you start assigning confidence levels. These range from very likely, say, 90–100% certainty, meeting multiple independent lines of evidence with no known abiotic explanation, down to very unlikely, less than 10%.
And where does something like just finding oxygen fit in?
Finding O2 in isolation, without other context. Under this framework, that's typically rated only inconclusive, because we know sunlight can make it on lifeless planets too.
Right. Context is everything. That's a truly comprehensive and cautious approach. Does it ever feel like maybe too cautious? Could we miss something?
That's an excellent question, and it's a tension scientists grapple with. The thing is, a single smoking gun biosignature that cannot be explained any other way is probably unlikely. And the history of science is, well, littered with exciting claims later explained by simpler non-biological processes. The goal isn't just caution for caution's sake, it's scientific robustness.
Because the stakes are so high.
Exactly. Declaring extraterrestrial life would be arguably the biggest discovery in human history.
Yeah.
You need to be as certain as humanly possible. That means ruling out everything else first.
Fair enough. So beyond K2-18b, what else has JWST been revealing about other exoplanets recently? Anything stand out?
Oh, JWST keeps delivering fascinating stuff. For instance, it found evidence of quartz nanocrystals, basically tiny grains of sand in the clouds of a hot Jupiter called WASP-17b. Tells us about cloud formation in extreme environments.
Wow, sand clouds.
Yeah. It also observed TRAPPIST-1b, the innermost rocky planet in that famous system.
Ah, the TRAPPIST-1 system. Lots of hope there.
Right. But for TRAPPIST-1b, the data suggests it has no significant atmosphere, which is a bit disappointing for life prospects there.
Okay, but what about the others in that system, the ones in the habitable zone?
Exactly. TRAPPIST-1e, F, and G are right in the habitable zone. Scientists are currently analyzing JWST data from those worlds, looking intensely for any signs of an atmosphere. Finding one there would be a huge deal.
Fingers crossed for that one. Okay, so our telescopes are amazing. They're giving us these incredible hints, detailed atmospheric compositions. But can we ever truly confirm life with just telescopes? Or do we eventually need to, get up close and personal?
That really hits the nail on the head regarding the limitations of remote sensing. Telescopes, even JWST, are observing globally average properties. We're looking at the entire planet's atmosphere or surface smoothed out.
We can't see surface details, right? Like continents or oceans directly.
Not yet, no. We certainly can't probe for microbial life hidden under the surface or in oceans.
Yeah.
So, for definitive answers, especially about biology, direct investigation using space probes seems indispensable.
So probes are the ultimate goal then for confirmation. Is that the scientific consensus?
I'd say largely yes. Our experience just exploring our own solar system with probes like Cassini at Saturn or the Mars rovers has shown time and again that probes reveal knowledge simply unobtainable from Earth-based or even space-based telescopes. Probes are needed to confirm what telescopes infer about things like planetary interiors, surface geology, evolution, and, crucially, possible biology.
Especially biology.
Yes. In astrobiology, direct investigation going there might be the only way to definitively follow up on those suspected biosignatures we might find in atmospheres. You really need in situ studies.
In situ meaning on-site analysis, looking for actual life forms.
Exactly. Literally. On-site biological analysis.
Okay, but getting a probe to another star, that sounds like pure science fiction right now. What are the major hurdles, the showstoppers?
Oh, the challenges are truly, truly immense. Let's start with just distance and time.
Yeah, light years are far.
Incredibly far. Even Proxima Centauri, our nearest neighbor with planets, is over 4 light years away. To put that in perspective, our Voyager 1 probe, launched in the 70s, took 37 years just to leave our solar system.
37 years just to get out? And how long would Voyager take to reach Proxima Centauri?
At its current speed, something like 100,000 years.
100,000 years. Okay, so clearly not feasible.
Clearly not. We need to go much, much faster.
How fast are we talking?
To get travel times down to decades, which still sounds long, but is maybe achievable spacecraft, would need to hit velocities around 0.1 CO. That's 10% the speed of light.
10% of light speed. The energy required for that must be astronomical.
It's almost unimaginable. Let's try to put it in perspective. Accelerating a useful scientific payload, say 100 metric tons, maybe like a space station module with instruments,
Okay.
to 10% the speed of light requires about 4.5 times 10 to the 19 joules of energy.
That number doesn't mean much to me. How much is that?
That's roughly half of the entire planet's current annual electrical generating capacity.
Half the world's electricity for a year. Just to launch one probe.
Just to accelerate it, yeah. The energy sources needed, we're talking nuclear fusion, maybe antimatter, or incredibly powerful Earth-based lasers. They all ultimately rely on collecting and processing solar energy on an absolutely enormous scale. Think hundreds of kilometers of solar arrays out in space.
Wow. Okay, that really drives home the scale. And the propulsion itself, how do you actually push something that fast?
We're deep into advanced, even theoretical concepts here. Things like nuclear fission or fusion rockets building on old ideas like Project Daedalus or the more recent Project Icarus study. Maybe antimatter propulsion, if we could ever make and store enough antimatter safely. Or laser-pushed light sails, which is another popular concept. All require huge engineering leaps.
It's fascinating that even the really cutting-edge proposals like Breakthrough Starshot, they still highlight these massive challenges, right? Tell us about that one.
Yeah, Breakthrough Starshot is a really ambitious idea. It proposes accelerating tiny, gram-scale nanocraft, they call them star chips.
Gram scale, like the size of a postage stamp?
Something like that, yeah. Attached to meter-scale sails that are incredibly thin, maybe just a few hundred atoms thick. And the idea is to push these sails with enormous ground-based lasers, maybe 10 to 100 gigawatts, accelerating the nanocraft to about 20% the speed of light, 0.2 C.
20%. That would get them to Alpha Centauri in, what, about 20 years?
Roughly,
Right.
yes. An incredible speed.
But what are the limitations? You send a postage stamp flying past another star at 20% light speed. What can it realistically tell us?
That's the core limitation, exactly. The very small payload mass means they'll be scientifically limited. They can maybe carry a tiny camera, some basic sensors. And critically, these probes, as currently conceived, would have no way to slow down at the destination.
No breaks.
No brakes. So it's just a super fast flyby,
Mm.
making detailed scientific studies incredibly difficult. They might only get fleeting images, basic readings. Honestly, they might not reveal much more than what our advanced solar system-based telescopes, like successors to JWST, might be able to tell us in a similar time frame anyway.
So speed isn't everything if you can't stop and look around.
Exactly. And there are other monumental challenges, too. Collisions with interstellar dust, for instance.
Dust.
That sounds harmless.
Not at 10 or 20% the speed of light. Even a tiny grain of sand hitting the probe at those speeds has the kinetic energy of a small bomb. It could destroy the nanocraft instantly.
Whoa, okay. Interstellar space isn't quite empty then.
Not at those speeds, no. And then there are communication issues. Time dilation means messages from Earth might take years to arrive, maybe even after the probe has already zipped past its target. Real-time control is impossible. So what does this all mean for confirming life? It really sounds like a very long, very challenging road ahead for interstellar probes.
It absolutely is. Transporting a scientifically useful payload, something weighing many tons, with sophisticated instruments that requires vehicles and propulsion systems so huge and powerful. Their construction and launch probably have to happen entirely in space, leveraging the materials and energy we can find within our solar system.
Building starships in space, basically.
Essentially, yes. And that presupposes a really well-developed space economy, a spacefaring infrastructure that could take decades, maybe even centuries, to fully develop.
Centuries.
Yeah.
Wow. But maybe finding a really strong hint of life with telescopes could speed that up.
That's the hope. The discovery of truly bona fide biosignatures, something really convincing seen through telescopes, could provide a massive boost. The incentive, the political will, the funding, it could really accelerate that industrial development in space needed for eventual interstellar travel. So we've embarked on an incredible journey in this deep dive, haven't we? From those distant glimmers of exoplanets in our telescopes, these subtle hints in starlight, all the way to the ambitious, almost daunting dreams of interstellar probes. The quest for life beyond Earth is clearly a multi-generational endeavor. Telescopes are our primary tool right now, incredibly powerful for discovery, for identifying potential habitability and finding those suspected biosignatures. But the ultimate confirmation of life, especially if it's complex life, that still seems to require direct in situ investigation. And that remains a truly formidable technological and societal undertaking for the future.
So as we continue to refine our amazing telescopic abilities and dream of these star-hopping probes, maybe consider this. Every new exoplanet we find, every tantalizing hint of a biosignature, isn't just another scientific data point, it's a stepping stone. It's slowly, surely bringing us closer to answering one of humanity's oldest, most profound questions: are we truly alone out here? It's really a testament to our insatiable curiosity as a species, and the just endless possibilities that lie out there in the cosmos waiting for us to uncover them, one deep dive at a time. Thank you for joining us.